Welcome back, everybody. So this is our third lecture on steady flow to confined wells. This is a really important lecture, so it's fairly short and hopefully pretty easy, not very complicated, but it's very important because the steps we take here to derive or demonstrate, how the steady flow to a confined well works are the same that we do for unconfined and for different example, even for the unsteady flow. So it's really important to sort of go through this a little slowly to introduce. Okay, so here's a depiction basically of well pumping into a confined aquifer. So on the left hand side here you have a little schematic of a well, and again this is taking an example of a casing, right? So a typical, American well, if you remember from that intro lecture. So there's a casing going down, there's some screen here, and you can see that our aquifer down here is confined, meaning it's at the bottom of some confining layer, and it's not linked to the atmosphere. So typically this is where the better quality water is, and there's no issue, so this is ideal. Now the question is, okay, when we pump this aquifer, what is the implication for the potentiometric surface? So again, remember that confined aquifers don't have a water table, they have a potentiometric surface, meaning their depth here, B, does not change, right? The depth doesn't change because again, since they're confined, there's no, dipping of the actual water level. The water level is constant. What changes is the head in the water, right? So when you're pumping it, what you change, and I'm sorry, this always does that. So when you're pumping it, what you change is the potentiometric surface here. So again, imagine this is your steady water level, this is your steady water level when you're not pumping. When you start pumping, obviously the water level drops in the well, and with the water drop in the well, what drops is the head, basically, or the potential surface, okay? So the potential surface, if there's no pumping, is somewhere here. So again, assumption of flat and stable and everything. And then when you start pumping, you're dropping the actual water in the well, but you're not dropping water in the aquifer, you're dropping the potentiometric surface. Okay, so you can see that the water is going to rush into the well from left and right, from everywhere, radial coordinates, from all around that well. Let's look at these equations. Okay, so we start where we always start, which is essentially a continuity statement, right? We're saying that whatever water you pump out of the well must come from somewhere, right? It must be equilibrated by flow into the well from the aquifer. So we can say that, so the flow into the well from the aquifer is the Darcy flux times the area. Again, if you didn't take the first course, I'm sorry, but you should really go back and take a look at those lectures on Darcy's law. So then when we write the Darcy flux as Darcy's law, so K, hydraulic conductivity, times the hydraulic gradient, and again, now we're in radial coordinate, right? So is dHdr, right? This is your Darcy's law for, when you replace X with R. And then the area here, so this is where the trick is important to understand. This area here is the area through which the water rushes into the well, meaning this is the area of the casing here, all the way around the screening, right? So this is the area of that cylinder, right? There's a cylinder here where the water comes in from all around. So the area we're looking for is that area all around the well where the water is seeping into the well, where that screen was in the previous picture, if you will. Now the area of this is, of course, the perimeter times the height of the cylinder. So it's 2 pi r for the perimeter at the top, and then b for the size, down. So this is the area around that sleeve, if you want, around the well where that water is seeping in. Now, if you understand this, you understand most of what you need. Okay, so now once we have this equation, and I'm sorry, I'm just cleaning up a bit here. Now that we have this expression, we can just do the usual mathematical trick where we separate the variables, right, and then we integrate. So separating the variables, we get dH on one side and then 1 over r dr on the other side, and then everything else is some constants that we bunch together here, right? So we have some constants, right, the hydraulic conductivity, the depth of the aquifer, B, the pumping rate, Q, right? These are all known numbers, if you will. And then we separate the variables, which are, again, 1 over r dr, and then dH on the left-hand side. Remember that Kb is the transmissivity of the aquifer, and that's typically what we want to know when we do wells tests or aquifer tests. So we can replace Kb with T, and this is the final expression. Now we can put an integral on both sides and solve. So obviously 1 over r dr is going to integrate to a natural log, right, ln. So, integral of 1 over x is ln x. So we do that, and then the integral of dH obviously is just h between, the 2 points. So now we get h between 2 points, natural log of r between 2 points. Again, remember that r2 minus r1 equals the ratio, right? Just by mathematical rules. So then this is it. Now we have an equation where we can, for example, find the transmissivity from 2 points, right? So if we have 2 points at different distances from our well here, let's call this H2 and H1, here and here. If we can measure 2 points with 2 observation wells at some distance from our pumping well, now we can actually calculate, for example, the transmissivity of our aquifer, which is typically what we want to know for water resources, right? How much water can we get? So again, remember, transmissivity is a normalized flow, basically. It's how much water can that aquifer give us per unit of head drop, right, or per pumping. Okay, so how do we use that? I'll just do a quick, simple example. Oh, before I do the example, one quick introduction of drawdown. So the drawdown and the radius of influence, these are 2 important concepts. So the drawdown is basically like the head difference, but it's really the water missing at the top. So the drawdown here is H0 minus H. So the drawdown is really, the amount of water that you pumped in the well. So the drawdown in the well is literally the difference between the stable level when you don't pump and, some level later. So that's the drawdown. And this is different because again, when we do head, right, the head is the height of the water, or, for an unconfined case is the height of water. For a confined case, it's just the potentiometric surface here. But it reflects the height from some datum, from the bottom of the aquifer, basically. But typically when we pump, we don't know where the bottom is, or we might not know where the bottom is. What we do know is where that, water surface is, or that water in the well that's easy to measure, right? So if you do a couple piezometers here and here, right, the water here and the water here, you can measure this easily, and the water here, you can measure this easily, and so it's easier to convert everything into drawdown, so meaning, depth to the water as opposed to, depth of water from some bottom that you don't know where it is. So again, it's basically the same, right, but it's just inverted. So now you can write that same equation as before, again, with the drawdown being the difference in head, from some point to another point. Now, if we write the drawdown as a function of distance, right, we can say that it is, so if we take the radius of influence, if we take a point where the influence of the well is 0, basically, so there's no more influence of the well on the either water table, or in this case, on the potentiometric surface for a confined case, right? So at some point far from the well, the pumping has no influence, like there's no drawdown, basically. Drawdown is 0. So that's what we call the radius of influence. So the radius of influence here, again, if you have an observation well that is sufficiently far from the well, there's a point where basically the well has no influence on the potentiometric surface, and that's the radius of influence of the well. And again, you can solve for this by setting your drawdown equals 0. Okay, so we'll do many examples of that, but this becomes pretty important. Okay, so here's our quick example to wrap this up. So a well is completed in a confined aquifer and pumped at some discharge, Q, 200 cubic meters per day. The drawdown is measured at 2 monitoring wells, which are 10 and 25 meters from the pumping well. So now we have those 2 observation wells, 10 and 25 meters from a well. The heads in the monitoring well stabilize, and they're measured at 86 meters and 82 meters in those 2 wells. So again, remember that these are now given in heads, not in drawdowns, right? So they're given as the depth of water seen into those observation wells, or if you will, the depths to the potentiometric surface. Now, if we solve this using our little equation for the transmissivity, right? So what is the transmissivity of the aquifer? That's typically what we want to know. Again, we have all the constants. We know Q, we know H2 and H1, we know the distance of those 2 wells, and so we know what the transmissivity is, 15 square meters per day. Okay, so this aquifer has a transmissivity of 15 square meters per day. Okay, I think this is it for today. Hopefully that was useful. Again, go back and watch this, with a rested head. It's really important that you understand the succession from the governing equation. So basically the mass balance with Q equals Darcy flux times area. Understand what that area is, where the water is seeping into, and then the steps, to derive these equations. Okay, thank you very much, and I'll see you in the next video where we do the same tricks but with an unconfined aquifer. Thank you.